You ready? Let's learn some math. Math, 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 math. Math, 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 math. Math, 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 math.
Come, take a journey with us each Monday from 5:30 p.m. on ABS TV. Let's get to the heart of the matter. Math matters. Welcome back to another episode of Math Matters. I'm your presenter, Mrs. Tisha Hughes Thornhill. Last week, we would have begun our lesson on matrices, and so today we're just going to continue that. But as you know, we're going to take a look at our challenge question from the week before. So let's solve that. So the challenge question reads, given matrices X, Y, and Z, calculate negative 2/3 y, and secondly, x minus 2z plus y. So beginning with negative 2/3 y, we will rewrite negative 2/3 and replace y with its matrix, which is 3, 0, negative 1, 6. And just as a reminder, this is an example of scalar multiplication. And so everything in the matrix will have to be multiplied by negative 2/3. So we begin with negative 2/3 times 3, then negative 2/3 times 0, negative 2/3 times negative 1, and negative 2/3 times 6. And we're going to just begin by working out the first position, which is the first row, first column, negative 2/3 times 3. So negative 2/3 times 3 is the same as negative 2/3 times 3 over 1. And we cancel in the direction of the sign. So 3 can go into 3 once. And so what we end up with is 2 times 1 over 1 times 1. And of course, that is negative, so our result is going to be negative 2. In our second position, we have negative 2/3 times 0. And we know that anything times 0 is 0. And so we don't need to show any work at the side for that. Going to our third position, negative 2/3 times negative 1. We're going to take it to our side work. And we'll notice that we can't cancel anything in terms of the numbers, but we do know that a negative times a negative gives us a positive result. And so we'll just multiply across the numerator and then across the denominator. So 2 times 1 is 2, and 3 times 1 is 3. And so our answer for that position would be 2/3. And in our final position, negative 2/3 times 6, we cancel again in the direction of the sign. 3 into 3 goes once, 3 into 6 goes 2 times, and so we multiply across the numerator. 2 times 2 is 4, and 1 times 1 is 1. That gives us 4 over 1, and we had a negative, and so that is negative 4. Part 2 reads x minus 2z plus y, and the 2z plus y is in brackets. And so we're going to begin with just replacing the letters with their respective matrices. So we will rewrite the question as thus. So because we have the bracket, we're going to need to work that portion first. However, when we look inside the bracket, we'll notice that we also have scalar multiplication happening. And so we will have to multiply 2 by matrix Z, which is negative 2, negative 1, negative 3, and 4. So we will have 2 times negative 2, 2 times negative 1, 2 times negative 3, and 2 times 4. So we'll just rewrite the first matrix, 5, negative 6, 0, 8, and rewrite the final one as well, which is 3, 0, negative 1, 6, while replacing the middle with the answer. So negative 2 times 2 is negative 4, 2 times negative 1 is negative 2, 2 times negative 3 is negative 6, and 2 times 4 is 8. Since we have the bracket still there, we haven't removed it, we would have to compute the addition. And so we can rewrite in our next line 5 minus negative 4 plus 3, because those positions are related. And so we just rewrite it with the bracket. And we'll do that for the first row, second column, negative 6 minus negative 2 plus 0. 0 minus negative 6 plus negative 1. And finally, 8 minus 8 plus 6. So we'll have to work the brackets, and we can rewrite each of these positions as 5 minus negative 1, because negative 4 plus 3 is negative 1. Second column, first row, negative 6 minus negative 2, because negative 2 plus 0 is negative 2. Second row, first column, 0 minus negative 7, because negative 6 plus negative 1, remembering when those two signs come together, it means to minus, and so that could also be said or rewritten as negative 6 minus 1, and so that will give us negative 7. And in the second row, second column, 8 minus 8 plus 6, 8 plus 6 is 14, and so we will have 8 minus 14. To simplify, 5 minus negative 1 is 6, because the two minus signs, or the minus and the negative, coming together means to add. And so that is essentially 5 plus 1, which is 6. Negative 6 minus negative 2 is the same as negative 6 plus 2, which is negative 4. 0 minus negative 7 is the same as 7. And 8 minus 14 is negative 6. Thank you so much for all of you who continue to email your submissions. When we return, we will continue our matrix lesson. But first, let's hear a word from our sponsor.
The Board of Education is responsible for the funding of scholarships, awards, and bursaries within Antigua and Barbuda. In keeping with our mandate, interested individuals who are citizens or nationals of Antigua and Barbuda are invited to apply. Application forms are available online at www.abboardofeducation.com and should be completed and submitted on or before the last working day in April of each year. Scholarships are available for those wishing to pursue an associate's, bachelor's, or master's degree locally, regionally, and internationally. Individuals reading for PhDs are also supported. We are the Board of Education. For more information, visit our website at www.abboardofeducation.com or call us today at 463-9025, 463-9026, 463-9027, or 463-9028.
Welcome back. Now let's take a quick look at when matrix multiplication may be used. Matrix multiplication is probably the most important matrix operation. It is used widely in areas such as network theory, transformation of coordinate systems, and population modeling, to name but a very few. Here we have a model of network theory and how that works. And this is something that's used for analysis purposes. Companies may use this to help identify and evaluate potential partners, customers, and competitors in different markets. By mapping and analyzing the structure and dynamics of their network, companies can find gaps, opportunities, and threats, and devise strategies to improve their network position and performance. Next, we have a very recent topic that we would have covered here, transformations. A matrix can also represent a transformation of a vector, so such as rotation, reflection, enlargement, translation. Also, here's another way that matrix multiplication is valuable or useful. This can be used in matrix population model, and this is a convenient tool for summarizing per capita survival and reproduction rates of a population. It can be used for calculating a finite population growth rate and generation time. Matrix multiplication is also used to represent and apply linear transformations in computer graphics, robotics, physics, and many other fields. So we're going to now take a look at compatibility, because can all matrices be multiplied to another? Or if we have two matrices, can they always be multiplied to each other? So we'll have to test for compatibility to ensure that it's even possible. So in order to successfully multiply matrices using matrix multiplication, we would first need to check their compatibility. Can they be multiplied by each other? Not every pair of matrices can be multiplied. If you have two matrices, the number of columns in the first matrix must equal the number of rows in the second matrix. So here we have two examples of multiplication, and we're going to test to see if they are in fact compatible. So for example, our first matrix to the left is a 2 by 3 matrix because it has 2 rows and 3 columns. The next matrix is a 3 by 3 matrix, 3 rows, 3 columns. And when we look at the number of columns in the first matrix and the number of rows in the second matrix, we'll notice that those numbers match. And so this would therefore mean that these matrices are compatible. They can be multiplied. Now, the result for this would therefore be the number of rows for the first matrix and the number of columns for the second matrix. So our result would be a 2 by 3 matrix. Let's take a look at the second example. We have the same 2 by 3 matrix from before, multiplied by itself, but we'll notice that the number of columns in the first matrix does not match the number of rows in the second matrix. And so therefore, this is not compatible, and so therefore cannot be multiplied. If two matrices can be multiplied, what would the new dimensions be? It would be the number of rows for the first matrix and the number of columns for the second matrix. So let's actually put this in action. We have 4 matrices, matrix A, B, C, and D. And we're asked to show whether the following are compatible or not. So we'll begin with AC. When we look at matrix A is a 2 by 2 matrix, and matrix C is a 2 by 3 matrix. Are they compatible? Yes, because the number of columns in the first matrix match the number of rows in the second matrix. And so that result would be a 2 by 3 matrix. Let's look at BA. Matrix B is a 2 by 1 matrix, and matrix A is a 2 by 2 matrix. Would they be compatible? No, they would not. And that is because the number of columns in the first matrix does not match the number of rows in the second matrix. Finally, DB. DB, well, matrix D is a 3 by 2 matrix, and B is a 2 by 1 matrix, and this would be compatible for the reasons we've been stating. And so the result for this multiplication would be a 3 by 1 matrix. Now that we've covered matrix multiplication compatibility, let's pause to hear a word from our sponsor. When we return, we will look at matrix multiplication.
The Board of Education is responsible for the funding of scholarships, awards, and bursaries within Antigua and Barbuda. In keeping with our mandate, interested individuals who are citizens or nationals of Antigua and Barbuda are invited to apply. Application forms are available online at www.abboardofelucation.com and should be completed and submitted on or before the last working day in April of each year. Scholarships are available for those wishing to pursue an associate's, bachelor's, or master's degree locally, regionally, and internationally. Individuals reading for PhDs are also supported. We are the Board of Education. For more information, visit our website at www.abboardofelucation.com or call us today at 463-9025, 463-9026, 463-9027, or 463-9028.
Welcome back. In the last episode, we looked at addition, subtraction, and scalar multiplication. And we just spoke about compatibility. So now let's get into matrix multiplication. In order for us to multiply a matrix by another, we would take the first row of the first matrix and then multiply it by the first column of the second matrix. We do this by multiplying the first entry in that row by the first entry in the column, second entry in the row by the second in the column, etc., until you finish. We previously checked to see if AC was compatible, and we know that we can in fact multiply them. So AC means that we're going to be multiplying matrix A by matrix C. Matrix A, we are concerned about the rows, and so each row in matrix A is going to be multiplied to each column in matrix B. So we'll begin with row 1, column 1. Row 1, column 1 would be 3 times negative 1 plus negative 2 times 5. So the first number is multiplied, the first number in the row is multiplied to the first number in the column and added to the multiplication of the second number in the row by the second number in the column. So again, that would be 3 times negative 1 plus negative 2 times 5. And we'll follow this pattern for each row and each column. So row 1, column 2 would be next. 3 times 0 plus negative 2 times negative 3. Row 1, column 3, 3 times negative 2 plus negative 2 times negative 3. We'll now move on to row 2. Row 2, column 1. 0 times negative 1 plus 1 times 5. Row 2, column 2, 0 times 0 plus 1 times negative 3. And finally, row 2, column 3, 0 times negative 2 plus 1 times negative 3. And we know the next step would now be to simplify what we have here in our matrix. And so we'll look at the first position, and 3 times negative 1 would be negative 3 plus negative 2 times 5. Negative 2 times 5 would be negative 10. So that would then be negative 3 minus 10. Next, 3 times 0, well, we know that anything times 0 would just be 0, is 0. So 3 times 0 is 0, plus negative 2 times negative 3. And negative times negative gives us positive, so that would just be 0 plus 6. 3 times negative 2 plus negative 2 times negative 3. 3 times negative 2 would be negative 6, and negative 2 times negative 3 is plus 6 or positive 6. 0 times negative 1 is 0, plus 1 times 5 is 5, so that's 0 plus 5. 0 times 0 is 0, plus 1 times negative 3 is negative 3, so that would be 0 minus 3. And 0 times negative 2 plus 1 times negative 3, well, 0 plus, or 0 minus 3, sorry, 0 minus 3. Now that we have less to look at, we can now come to our final answer for this matrix multiplication. Negative 3 times negative 10, negative times negative is positive, and so, sorry, not times, negative 3 minus 10, I read that incorrectly. Negative 3 minus 10 would be the same as, signs are the same, so we add and keep the sign. So that would be negative 13. 0 plus 6 is 6. And negative 6 plus 6 is 0. Because when the signs are different, we subtract and keep the sign of the greater. But in this case, they're both 6. And so 6 from 6 is 0. 0 plus 5 is 5. And 0 minus 3 is negative 3. And finally, again, 0 minus 3 is negative 3. And so our answer for AC would be negative 13, 6, 0, 5, negative 3, negative 3. So using the same four matrices, we are going to now look at AB. So we're doing another matrix multiplication. Matrix A is a 2 by 2 matrix, and matrix B is a 2 by 1 matrix, and so we know that this is compatible, and so we can continue with our multiplication. Matrix A times matrix B, we follow the same procedure, row by column. And so that would be 3 times 11 plus negative 2 times negative 4. And there's not another column for us to multiply by, and so we move on to row 2 by the same column. 0 times 11 plus 1 times negative 4. And now we'll simplify. 3 times 11 is 33, plus negative 2 times negative 4. Negative times negative is positive. 2 times 4 is 8. So that becomes 33 plus 8. 0 times 11 is 0, plus 1 times negative 4. 1 times negative 4 is negative 4. And so that is 0 minus 4. 33 plus 8 is equal to 41. And 0 minus 4 is equal to negative 4. Let's take a break. And when we return, we will wrap up by taking a look at the inverse of a matrix.
The Board of Education is responsible for the funding of scholarships, awards, and bursaries within Antigua and Barbuda. In keeping with our mandate, interested individuals who are citizens or nationals of Antigua and Barbuda are invited to apply. Application forms are available online at www.abboardofeducation.com and should be completed and submitted on or before the last working day in April of each year. Scholarships are available for those wishing to pursue an associate's, bachelor's, or master's degree locally, regionally, and internationally. Individuals reading for PhDs are also supported. We are the Board of Education. For more information, visit our website at www.abboardofeducation.com or call us today at 463-9025, 463-9026, 463-9027, or 463-9028.
Welcome back. Let's continue with our lesson. The inverse of a matrix. Here we have matrix A, and this time we would have used letters to represent the various numbers that they could possibly be in each position. So we have A, B, C, D. The inverse of a matrix is usually written as seen on the screen, A to the power of -1. It's read A inverse. And this is equal to 1 over the determinant of the matrix times the adjoint of the matrix. But what is the determinant and what is the adjoint? The determinant is found by multiplying A times D minus B times C. And so if you notice, the letters correspond with the different positions of the matrix. The adjoint would then be, and this is interesting, so take note. I think this is one of the easiest ways to remember how to position the adjoint. So the first shall be last, the last shall be first. Change the signs of the other two. And so the first, which is A, becomes the last, which is D, becomes the first, and B and C remain in their positions. However, if we notice in the original matrix, B and C are positive, and so those signs are going to change. They would therefore become negative. The first shall be last, the last shall be first. Change the signs of the other two. If the determinant equals 0, then the matrix is considered to be singular. That means the matrix does not have an inverse. So let's compute a matrix A that actually has numbers now. So matrix A, 3, -2, 0, 1, and we're asked to find the inverse of this matrix. But let's remember that A inverse, or the inverse of any matrix, which we just happen to be using A, is equal to the 1 over the determinant of the matrix times the adjoint of the matrix. And we can express that as the determinant, again, AD minus BC, and the adjoint as we would have previously recapped. So let's look at matrix A, 3, -2, 0, 1, and we're going to find the inverse of that. So this would be 1 over the determinant, which is 3 times 1, minus 1 over the determinant, and the determinant is 3 times 1 minus negative 2 times 0 times the adjoint. So 3 is first, so it becomes last. 1 is last, so that becomes first. And we have negative 2, which will then become positive 2. And we have 0, and so that still remains 0 because there is no such thing as negative 0. And we will just simplify our denominator. 3 times 1 is 3 minus negative 2 times 0, which is 0. So we'll have 3 minus 0. And so that gives us 3, which therefore means that our determinant would be 3 and would be written as 1/3 times the adjoint. We're not done here because this now should look familiar. This is another example of scalar multiplication. And so we are going to multiply everything in the adjoint by 1/3. So we have 1/3 times 1, 1/3 times 2, 1/3 times 0, and 1/3 times 3. And you know, we've been doing this for quite a while, and so we're not going to have any side work here because we should be a little bit more versed with carrying out these computations. So 1/3 times 1 is going to be 1/3. 1/3 of 2, or 1/3 times 2, is going to be 2/3. 1/3 times 0 is 0. And 1/3 times 3 is 1. And that's it. That's it for the inverse. That's all there is to it. We just have to remember the form, which is 1 over the determinant of the matrix times the adjoint of the matrix. Next, we're going to talk about if we multiply a matrix by its inverse. So the original matrix, if we multiply it by the inverse, we will always get the identity matrix. Now, what is the identity matrix? The identity matrix of, for example, a 2 by 2 matrix would look like this. And when we multiply, the identity matrix in the diagonal would be 1. So it's made up of just 1s and 0s. And by definition, the diagonal is going from top left to bottom right, and those elements are always going to be 1. Every other space is going to be filled with 0. And so a 3 by 3 identity would look as seen. So the identity matrix is a diagonal matrix where the elements are 1, and the diagonal matrix is a square matrix. And a square matrix just simply means that it has the same number of rows and the same number of columns. Here we have our challenge question for this week. We have 2 matrices, L and M. And the question reads, given matrices L and M, calculate LM and finally M inverse. We really appreciate your commitment in joining us Monday after Monday and engaging in our challenge questions. Please make your submissions to our email address at mathmatters268@gmail.com. Once again, our email address is mathmatters268@gmail.com. Thank you for staying with us until the end, and good evening. See you next week when Mr. Lennon will be sharing a lesson on vectors.
Learn some math. Math, 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 math. Math, 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 math. Math, 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 math.
Come, take a journey with us each Monday from 5:30 p.m. on ABS TV. Let's get to the heart of the matter. Math matters.